unsaturated hydrocarbons are essentially hydrocarbons that basically have at least a excuse me, at least a double bond or a triple bond. And again, by them having either that double bond or that triple bond, what that does is essentially you have to lose two hydrogens to make those extra bonds. And that means that they end up not having the maximum number of hydrogens that they should. And that's basically what an unsaturated hydrocarbon is. Saturated hydrocarbon is like our alkanes, which are all single bonded carbons, and they have the maximum number of hydrogens they should have, based on how many carbons are there. So again, every time we sort of make that double bond or triple bond or sort of add a bond, we do have to sacrifice a couple of hydrogens. Otherwise, our carbons will end up with too many bonds to them and more than four bonds, and obviously more than 8 electrons ultimately. So when we go to name alkenes, which are guys that have a functional group of a carbon-carbon double bond, are alkynes, which have a carbon-carbon triple bond. We basically do the same thing as we did with our alkanes. So always pretty much in organic naming, we're always looking for the longest continuous carbon chain. Now, since these things do have double bonds or triple bonds, we're looking for the longest continuous carbon chain that does contain the double bond or triple bond. So they do have to contain that double bond or triple bond. And once you do that, it will again match one of those 10 alkanes that we talked about earlier. And the difference is we do change the ending of the name. So either ENE for our double bond, YNE for our triple bond. Also, once we get about usually around four or more carbons involved when you have a double bond or a triple bond, you do need to actually give the location as to where you can find the double bond or triple bond on the chain. And we want to give the double bond or triple bond really the priority in terms of numbering. So whichever way gives that double bond or triple bond the smaller number, that's the way you want to number the chain. And then every group that's attached will be numbered accordingly, again, in alphabetical order. So I think we did some examples at the end there of drawing and also naming. So let's just take a look at these couple here that we got up here on the screen. So again, here we do see a double bond. We want to count all of our different ways to try to get ourselves the longest continuous carbon chain with the double bond. So we got 1, 2, 3, 4, 5. We could go up 6 and 7. We could also go same starting point, 1, 2, 3, 4, 5, and then go down. Also gives us 6 and 7. We could even start up here, I think. 1, 2, 3, 4, 5, 6, and 7. So it looks like you could go a wide variety of ways, but it does look like 7 is our longest continuous carbon chain. And as we've talked about a couple of times as we've been doing this, sometimes it's just easier to kind of take the straightest or a straight type chain when you're trying to figure out the main part of it. Kind of sometimes makes it easier to see everything else. So I'll just take kind of straight and then go up. So we'll call this here the main part of the chain, which again does have 7 carbons. So 7 is based off of heptane. It has a double bond. So our heptane becomes heptene, ENE, because of the double bond. We then want to number the chain, whichever way is going to give that double bond the smaller number. And if we went left to right, we would have 1, 2, 3, 4 for our double bond. If we went right to left, it'd be 1 and 2 in terms of our double bond. I'm sorry, 2 and 3, if I could count 1, 2, and 3 for our double bond there. So we do want to go right to left here in this particular case. So this would be 1, 2, 3, 4, 5, 6, and 7. And again, the purpose of that, it does give our double bond the smaller number. So we do want to add that to our name, 3-heptene. Again, the 3 is the location of our double bond in this particular case. Now, we want to then look and see what groups we have attached. So right here, we have a 2-carbon group, and that is an ethyl group. Over here is a 1-carbon group, which again is our methyl group. And because we did have to lock everybody in terms of the numbering here because of the double bond, that is how we will number these groups. So we will have something like 3 ethyl, dash 6-methyl. 3-heptene. Again, the 3 coming here for where our ethyl group is located, and the 6 coming here for where our methyl group, alphabetical E before M. And again, a reminder that we put a dash between numbers and letters, and we put commas between 2 numbers. Any questions on that name right there?
Yeah, I had a quick question.
Yeah.
How you went through 1 through 7?
Yeah.
Why didn't you go the other way since methyl is probably closer?
Yeah. So in these, guys, when you have basically a double bond or a triple bond, or really whenever you have sort of a functional group, you want to give that functional group the smallest number, so they kind of take the priority in terms of numbering. So if we did go the other way, it'd be 1, 2, 3, 4, 5, 6, and 7. And the one that gets the priority here is the double bond. So if we went sort of that left to right way, our double bond would end at carbon number 4, or start at carbon number 4, as opposed to carbon number 3. So that's why we chose to actually go the other way, the way that we did, because it actually gave the functional group, which is the double bond, the smaller number. So you always kind of want to shoot in terms of sort of priority is functional group when you number the chain should usually get the smallest number. And then if there's a tie, in terms of whichever way you went, perhaps it was say 4 either way, then the next important thing would be the groups. And we really don't have that sort of issue with alkanes because alkanes, even though carbon-carbon single bond is the functional group, that technically really isn't. So with the alkanes, it's always the groups attached to give the lower numbers. But here, when we have double bonds or triple bonds, they should always get the lowest number.
Okay, thank you.
You're welcome. Other questions? Let's see here. I would say most people that UPAC name way of doing it will put the 3 in the front and not necessarily right there. Some people will kind of do it that way, but for our class, you should probably do it the way we did it here, without the kind of 3 in the middle. So I can say no in that sense. It's just the way we should probably name it for this class. Okay, but you will occasionally see people kind of do it like that with the number kind of in there at the end. Other questions? Okay. So let's take a look at the bottom one, which again, this one looks pretty straightforward. It looks like just the straight across here is going to be our longest continuous carbon chain. And we got 1, 2, 3, 4, 5, 6 there, it looks like. So 6 is going to be based off of hexane. Because this has a triple bond, we drop the last part and we do get the YNE at the end of it. Again, here, same as was the question earlier, we do have 2 ways of doing the numbering. We could go left to right, which gives us a 1, 2, 3, 4, 5, and 6. We also could go right to left, which would give us 1, 2, 3, 4, 5, and 6. Now, in this particular case here, if we number left to right, our triple bond ends up at carbon 3. If we go right to left, it also ends up at carbon number 3. So as we were just talking about, the triple bond here should get the priority in terms of the numbering. But in this particular case, it doesn't matter which way you go in terms of the triple bond because you get the same number. So the next thing we want to look at is what is next, what is important sort of next? What is the next important thing in terms of numbering? And that would be the location of the group in this case. So since it doesn't really make a difference as to which way you go for the triple bond, the next important thing would be we would want to give this group the smaller number in this case. And that would mean that we would want to number left to right. So giving this group would be carbon 2. Going the other way would be carbon 5. So we would want to number the top way here. And that does give us 3 hexene, again, for the location of the triple bond. And that also now gives our group the smaller number, which would be 2 bromyl 3 hexene. Any questions on that name? So kind of like the question that was just asked, again, in this particular case, the functional group, it really doesn't matter which way you go. So then you want to look at the next important thing, which would be the actual groups attached. And here we see that it does make a difference in terms of the group, given this group, the smaller number going left to right. Any questions on how to name these guys or draw them like we talked about? Okay. So let's take a look at a few more examples, I think. So we do have some haloalkenes. So remember, guys that have halogens, as we talked about, we name it chloral for chlorine. If the group's bromine is bromo, fluoral, and so forth. So if we kind of go here, they were nice enough to highlight everything here in terms of her longest carbon chain. So this guy's got 1, 2, 3, and 4 carbons. Also a double bond. So 4 carbons is butane, and a double bond makes it butene here. Again, the location of our double bond, 1, 2, 3, 4, are going the other way, 1, 2, 3, 4. Again, does not make a difference in terms of the double bond. It is 2 no matter which way you go, but does make a difference for our group attached. And to give this group now the smaller number, because there's no difference for our double bond, we would want to number this way. And that would give us our 2-chloral, 2-butene in this particular case. Again, looking over here at the one next to it, 1, 2, 3, 4, 5, 6 carbons. In this case, we have a triple bond. So that is going to be hexyne. And in terms of numbering, 1, 2, 3, 4, 5, 6, or we could go the other way, 1, 2, 3, 4, 5, and 6. Again, here, the triple bond does not matter. It is 3 no matter which way we go. So we will put that 3 in there for the location of the triple bond. But again, here, the group attached, it does matter. And again, where we want to go left to right, as it gives it a smaller number. So this would be 2 bromo, 3 hexyne. Any question on those first 2 there? All right, continuing on here, we got 1, 2, 3, 4, 5, 6, 7, 8 carbons. 8 carbons based off of octane is a double bond, so it becomes octene. And in terms of our numbering, we do want to actually number left to right here. Again, going left to right gives our double bond carbon 3. If we went right to left, 1, 2, 3, 4, 5. So giving our double bond the priority and the smaller number, we would want to go that way. And it would be 3 octene for the location. In this case, we actually have a couple of methyl groups. So because we have 2 methyl groups, that's going to give us a dimethyl because there's 2 methyl groups in there. And the location is going to be based off of our numbering. So we have a methyl at carbon 2, and it looks like a methyl at carbon 6. So that's going to give us 2, 6 dimethyl 3 octene. Again, we do need to give locations of both of the methyl groups. And remember that when we go dimethyl, doesn't necessarily mean that they're on the same carbon. It just means that you have 2 of those in the entire molecule. Any questions on that name there? And lastly here, we got, looks like 1, 2, 3, 4, 5, and 6 again. But here we do have a double bond. So that's going to be hexane, which becomes hexene because of our double bond. Double bond is going to be a carbon 1, 2, 3, or 1, 2, 3, no matter which way you go. So because it's sort of a tie there for our double bond, it is going to be 3. We want to decide which way we should go for our groups in this particular case. And that's going to give our groups at carbon 3 and carbon 4. Also, in this particular case, doesn't matter which way you go on that. So that's going to be something like 3 chloral. As I run out of room, I'll go underneath. 3 methyl, 3 hexene. So I'll write it up here. It's 3 chloral, 3-methyl, not 3-methyl, 4-methyl. Sorry. Hang on here. 3-chloral 4-methyl. That should have been a 4. And 3-hexene in this particular case. So the way we really would want to go, since it does sort of alphabetically make a difference, even though the groups are both at 3 and 4 in this particular case, we would actually want to number the top way. Again, the top way here will give our chlorine, which is alphabetically first, the lower number. Putting the methyl with a 3 would give it obviously a higher number in terms of alphabetical. So in this particular case, we would want to actually number the top way. Any questions on naming any of these guys here? Okay. So then we're going to talk about some isomers here and talk about a special type of isomer, which is known as a cis or trans isomer. And isomers, if you remember, are really the same molecular formula, but sort of different connections. And when we do put sort of a double bond on that carbon-carbon bond, it actually restricts the rotation of the carbon. So in a single bond sort of situation, really the groups are free to just freely rotate around and around in the carbon. And that's why when we draw things, it really doesn't matter if you draw the group up or draw the group down, because there's kind of free rotation. When we put a double bond or even a triple bond in there, it sort of locks everybody into place, and those groups on the outside no longer can freely rotate around sort of the carbon-carbon axis. And what that creates is a new type of isomer, which is known as a cis or trans isomer. And basically a cis isomer is what happens when we get the groups on the same side. So a cis isomer is when we have two groups that are on the same side of the double bond. So here's our double bond. Here's a methyl group and a methyl group. They're both hanging out on the above the double bond, if you will. And that's what is referred to basically as the cis isomer. The trans isomer is when we have two groups that are on opposite sides of the double bond. So here's our double bond. And here's our methyl group. One's on top of the double bond, one's below the double bond there. They're on opposite sides, basically, of the double bond. And that is what is referred to as being trans. Now, can we have a cis and trans isomer every time we have a carbon-carbon double bond? And the answer is no. So in order to really have a cis or a trans isomer, a couple of things has to sort of happen. First off, when you look at the carbon-carbon double bond, there needs to be a group on each of those carbons that are the same. So you need to at least have a group that's the same on each carbon. And you can also need to have on the same carbon two different things. So for example, on the carbon on the left here, I have an A and a B, which are two different things. Carbon on the right, I have an A and a B, which are two different things. And I also have a group that's the same on both carbons. Also actually have two groups that are the same on both carbons. When we look at groups, especially when identifying cis and trans isomers, we can think of a hydrogen, even though we don't typically think of it as a group, as sort of a group as well. Now, that's important to make sure that you do have all of those things. So that what that means is, for example, if we isolate the carbon-carbon double bond, I look at the carbon on the left here. This has a methyl group and a hydrogen. These are two different groups on the same carbon. When I go to the right-hand side, I have a methyl and a hydrogen. Also, two groups that are different on the same carbon. When I look at the two different carbons, we also have the methyl group and the methyl group, like we talked about, which are the same. We also have the hydrogen and the hydrogen group, which are the same groups. So that's what we want to look at here, is basically need two different ones on the same carbon, but you need the same guy on opposite carbons. So for example, if I had A and A here. As soon as I look at this carbon that has two of the same groups, we cannot have cis or trans. So cis or trans cannot happen if you have a carbon that has the exact same group on it in a double bond. So it's always a double bond you want to look at when you do that, and try and identify them. So let's take a look here. That's basically what we just talked about. So here's again what we're talking about. We want two different groups on each carbon and at least a group that's the same on alternate carbons there. So let's see here. So if we look at this, for example, here, if we isolate this carbon-carbon double bond, we have one group here and this group, which are different, so that's good. But we have this hydrogen and this hydrogen, which are the same, so that eliminates the possibility of cis or trans. So again, as soon as you kind of see the same group, you cannot have, or cis or trans isomers to occur. So stereoisomers are isomers that differ only in their sort of three-dimensional arrangement. Constitutional isomers differ in the way the atoms are bonded to each other. So if we look at the 1-butene and the trans-2-butene here, these are constitutional isomers. They are different in the way that they are attached. Here, the CH2, CH3 are all together. Here, they're a little bit different. And these are constitutional isomers, again, same deal, but these are stereoisomer, these two guys right here, basically. And that's cis-2-butene and trans-2-butene as well. Again, these all have the exact same molecular formula, but different sort of connectivity, so they are isomers. Now, you may be wondering, I only see two carbons in a row, which oftentimes happens when people look at this and want to give a name. But you got to remember that you are still looking for the longest continuous carbon chain. And again, this would be 1, 2, 3, and 4. So this part right here is actually the longest continuous carbon chain, even though they drew it based on sort of the isomer. And 4 carbons with a double bond is butene, and 2-butene is the location of that. And as you can see, they put cis down in front to indicate that it's the cis isomer because group here and group here, same side of the double bond. Now, same thing here. If we were to name this guy, this again would be carbon 1, carbon 2, carbon 3, and coming down this way would be carbon 4. And again, that would still be butene, still be 2-butene for the location of the double bond. But now our group is one's above the double bond, one's below the double bond. They're on opposite sides. So this is trans 2-butene. And by the way, this would be 1, 2, 3, and 4, also butene, except double bond is located at carbon number 1. And here we have two groups that are the same. So we cannot have any cis or trans with this guy. Any questions on that there? Okay. So let's see here. Why don't you take a couple minutes here, look at each of these and decide whether they are cis, trans, or neither for A, B, and C on the bottom here. So take a minute or two and see what you come up with. Okay, so let's take a look here. So on all these, really where you want to look is when trying to figure out cis or trans is really that carbon-carbon double bond. That's really where you kind of want to focus in on. And you want to first make sure that when you look at it, that attached to the same carbon, you have different groups. So here I have a methyl group, I have a hydrogen. Those are two different groups. On the other one, this is actually an isopropyl group happening here, and that is a methyl group happening there. And those are two different groups. We then want to make sure and see if we have a group that is the same on opposite carbons. So on opposite carbons, we have a methyl group here, and on the other carbon, we have a methyl group here. And those are opposites of each other in terms of the double bond. That means that number one, or number A here, should be our trans isomer. Any questions on that one? Same thing here. We're going to look at our carbon-carbon double bond for B. We have a chlorine and we have a methyl group on the left carbon. So those are two different groups. We have an isopropyl group here on the right carbon, and we also have an isopropyl group here. And these are two of the same groups on the same carbon. That automatically eliminates the possibility of a cis or trans. So this would be neither in this particular case. And lastly, for C, looking at the left carbon, we got a hydrogen and we got an ethyl. On the right carbon, we have an ethyl and a hydrogen. So these are two different groups on each of the carbons. Now on opposite carbons, we have an ethyl group that's the same, and we have an ethyl group that's the same, and they are on the same side of the double bond. So this would be a cis. You could also look at the hydrogen if you really wanted to, also on the same side of the double bond. Any questions on that particular one there? Now, remember that if you do have something drawn like, say, the first one here, and if we wanted to name this guy, we want to look for the longest continuous carbon chain. And that would be perhaps 1, 2, 3, 4, and 5 would be our longest continuous carbon chain. We went 1, 2, 3, and down is 4. 1, 2, 3, 4, 5, and up is 5. So it looks like 5 is our longest continuous carbon chain. So the name of this guy, the base of this guy would be 5 carbons, and that is going to be based off of pentane. There's a double bond, so that's going to be pentene, E-N-E. Location of that double bond would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Double bond looks like number 2 would be the smallest number. Then we would actually have a methyl group at carbon 4 and a methyl group at carbon 3. So this would be 3, 4 dimethyl 2-pentene. And since we identified this as trans, this would be trans 3, 4 dimethyl 2-pentene. So again, very common when people see it sort of drawn as cis or trans. They really just focus in on that double bond in the middle and think everything else is a group. You still want to look for that longest continuous carbon chain and make sure that you sort of get the correct name there. Any questions on that? Okay. So for these, why don't you give the name of each of these, do cis or trans, and see what you come up with. So take a couple minutes and give it a go. Okay, let's take a look here and see. So first off, we'll start with the cis or trans part. So we do want to focus in on our double bond area. We do have different groups attached there, so that's good. We do have different groups attached here, so that's good. And on opposite carbons, we do have groups that are on the same side. So we do know this is basically our cis isomer. Longest carbon chain is actually 2 carbons. So 2 carbons based off of ethane, and it becomes ethene. We have a group at carbon 1 and 2 in this case. So this would be cis 1,2 dibromo ethene as the whole name here, again, with our 2 carbons and our 2 bromine groups. Coming down here, again, focusing in on our 2 carbons that are there. We do have one group here and one group here, which are different, which is good. We have one group here and one group here that is different, so that's good. We do have a group that is the same on opposite carbons, and they do look like on opposite sides of the double bond. So this would be trans. And in terms of the longest carbon chain, again, here it actually would be 1, 2, 3, and 4 in this particular case. And 4 carbons is butene. Location of the double bond is carbon 2, no matter which way you go. 1, 2, 3, 4, or 1, 2, 3, 4. So this is 2-butene. This is trans 2-butene in this particular case. Remember that when we're naming it, hydrogen is not considered a group, although it is kind of considered a group when you're trying to determine cis or trans. Lastly, here, focusing in on our double bond, we got a group that's this here and here that are different. We have a group here and here that are the same group, and that means that we cannot have a cis or trans here. Again, it's because we have 2 groups on the same carbon in that double bond that are the same. That eliminates the possibility of cis or trans. But our name here would be 1, 2, 3 carbons, and a double bond would be something like propene, and a carbon 1 here. We have those 2 groups, so that would be something like 1,1 dichloryl propene. Don't really need a numbering because it's not really 4 carbons. So wherever that double bond is will be carbon 1. But again, no cis or trans on this one because of the Cl that we see there. Any questions on any of those there? Now, one last thing in terms of if you're asked to sort of draw something. So let's say, for example, you were asked to draw cis 3-hexene. And sometimes people struggle with sort of how to draw it, to look correct in terms of cis or trans. So I usually recommend that you kind of ignore the cis or trans part first off if you need to draw it, and really just draw it like we kind of drew everything else, which means we would start in the back and kind of go this way. And 6 carbons is how much hexene would be. So I'm just going to erase this so I got somewhere to scribble on this page here. There we go. All right. So we would draw our 6 carbons just like kind of normal. 3-hexene means that if we go to carbon number 3, so if I went left to right, 1, 2, and 3, we would have our double bond there. And everything else here would be hydrogens, and we would fill it in like normal. And what I'm going to do is at the double bond, I'm just going to kind of draw a hydrogen for now, and we'll do that. And over here, this guy would get a hydrogen, and the rest of it would be CH2, CH3. So I would recommend drawing it just straight like you normally would. I would probably draw out the hydrogens on the carbon double bond. Then what I would recommend doing is going back and just kind of putting a box around the carbon double bond and start with that for your drawing. And when you kind of do the first drawing, what that allows you to do is really kind of focus in on what the group should look like. So off of this carbon, I have an ethyl group. Off of this one, I have a hydrogen. Off of this one, I have a hydrogen and also an ethyl group. So since this is cis, I want to put my ethyl groups, for example, on the same side. So I could just draw my ethyl group going up if we like, and put the ethyl group over here going up. And that would put my hydrogens going down. And you could really kind of easily draw it the correct way by sort of doing that, isolating the carbon-carbon double bond, and then putting that, rather than trying to figure out, okay, do I need to kind of swing this up, swing this down? It's a lot of times a lot easier to kind of do two drawings, one just like you did before. The only additional thing is, like I said, when you get to that double bond, I would draw out the hydrogens that are attached there, because they may be groups that you need to sort of accentuate in your outer drawing there to show the cis or trans in this particular case. Question on how to draw that there. Okay. So then let's talk about these alkenes and reactions that they undergo. So alkenes basically will undergo what is referred to as really an addition reaction. And in an addition reaction, very much like it sounds like, we're essentially going to add both of these things in. Right? So both of these guys will get added. And where they get added is always right here. So it's always that functional part of the molecule. It's the carbon-carbon double bond is pretty much where it gets added. Now, when we go to add these guys, say the X and the Y, whatever that may be, we cannot just directly slap an X up there and slap a Y up there, because if we do, we now have way too many bonds to our carbon. Carbon now has 5 bonds. So in order to basically allow both of those things to add in, we have to break the double bond. So what happens is the double bond becomes a single bond. And then basically you just add one to one carbon and one to the other carbon. So a very simple example would be something like this. If we had, say, this. And we want to add, say, Br2. It's basically Br2. So again, when we draw these reactions, pretty much absolutely nothing here is going to change, except that our double bond will become a single bond. So you literally could just redraw it exactly the way it looks. And all you got to do is just make that double bond into a single bond, and everything will look exactly the same. And now what you can do is, because you have room, you could put one bromine on one carbon and one bromine on the other carbon. And we will now have really our product here. Now, in this particular case, you could not screw it up because they are both the same. So they're both bromines here. And whenever you're adding anything that is basically the same, so Br2, Cl2, H2, these are where sometimes referred to as a symmetrical addition reaction. And that's just a fancy way of saying you're basically adding the same element to each side. So you really can't, like I said, mess that up. You can do that pretty easily. There's also some unsymmetrical ones we'll talk about here in just a second, but that's really what you want to think about here. You have an alkene, you have something you're adding to it, double bond, make it a single bond, and then one guy goes to one carbon, one guy goes to the other carbon, and that's pretty much all they wrote on that. When we do this with H2, this is sometimes what is referred to as a hydrogenation reaction, because we're adding H2. Same deal. And again, it does not matter how many carbons you got kind of going on. You know, it's all going to be kind of the same deal here. I'll just draw out the hydrogens there. And if we add H2, which is again, basically that H2. Sometimes you'll have a catalyst written on top of the arrow, like platinum or palladium and stuff like that. But again, the only part of this molecule, even though it may look really long, that's going to change is right here. And again, what's going to happen is double bond's going to become a single bond. So you literally could redraw it very quickly, just copying exactly what is there. And we're going to make our double bond into a single bond. Everything else is the same, including the hydrogens that were there to begin with. And now what's going to happen in this case is we're going to add one hydrogen to one carbon and one hydrogen to the other carbon. So I'll put those as blue, hydrogen here and hydrogen here. And that is obviously where the double bond was originally, is where we're doing that. And that is our product. So remember, when we look at these reactions, like I said, essentially, they're exactly the same thing. People always want to do all kinds of crazy things. There's really not a lot of crazy things that happen. Pretty much you just got to find that functional group part, and that's the part that changes. Everything else remains exactly the same. Any questions on that? This is also a symmetrical addition. Again, we're adding basically H2, which is the exact same guy. Here's another example. And again, if we look at it, absolutely nothing is changing here. We're going to look at our carbon-carbon double bond. It now becomes a single bond. We have 1, 2, 3, 4 hydrogens to begin with. 1, 2, 3, 4 hydrogens, and we put on 2 new hydrogens over here. Exactly. So in these type of reactions that involve alkenes, it is only that carbon-carbon double bond is the only place that changes. And that's exactly where it gets added to. Everything else remains exactly the same. Like I said, even if there's like, a ton of them, a ton of carbons, everything else will remain the same. It is just this part where we have that double bond that's going to basically change. Other questions on that? Uh, you technically could write CH2. I'm assuming you're talking here and here. You could write CH2 if you wanted to, especially if it just says draw the condensed formula. Sometimes people will draw it out because that's kind of the part of the molecule that changed, so you could kind of see what kind of got added on there. But yeah, it would be perfectly fine if it said, draw the condensed formula and just did CH2. CH2 would have been okay on that one. All right, so why don't you try some of these here, see what you come up with. All right. So draw the products of each of these reactions and see what you end up with. Okay, so when we look at this, and again, I just redrew it above it, sort of with all the hydrogens out, so you could kind of see it. You don't necessarily have to do this, but it might make it a little bit easier for you to see. Although there's a lot of carbons, a lot of stuff going on, we really just want to focus right there at the carbon-carbon double bond. And we know what's going to happen is essentially it's just going to become a single bond. We could draw everything exactly the same. So again, if we wanted to draw everything out, it would look exactly like this, like we started with. Again, the only main difference, double bond will now become a single bond. We'll still have the hydrogens that are there. Everything is exactly the same. And now that we've made room for it, we can now add our hydrogens in. And again, one hydrogen to one carbon, one hydrogen to the other carbon, and that would be our product. Again, here in terms of condensed formula, it would be something like this. Any question on that particular one there? Now, if we look at this guy here, again, if we drew out the hydrogens just to kind of get a visual of what's going on here, we have two hydrogens there. We have two hydrogens there. We have technically two hydrogens there. This guy actually has one hydrogen. This one has one hydrogen. Now, what's important here, even though it's a cyclo structure here, we are just going to focus in right there on our double bond, and exactly the same thing is going to happen. Our double bond will become a single bond. So we would literally just redraw it without the line. That would imply that a single bond has now been made. And then one carbon that had the double bond will get a hydrogen. The other carbon will also get a hydrogen here. And we will end up with this. And again, if you did not want to draw out all the hydrogens, it would look just like that. Any questions on that there? So double bond to a single bond, add one to each side, and you should be good to go on that. These are, again, all symmetrical additions. We're adding the exact same element to each side of the double bond. Now, while I'm thinking about, let's see here. While I'm thinking about something with a double bond, I think we talked about it last time in terms of naming, but let's just make sure. Let's say we did have this guy to start with. And let's say we had our double bond here. And let's say we had a CH3 group here. If we wanted to name this, this would be cyclopentene. Again, 5 carbons, which is pentene with a double bond. Cyclo because it's a ring structure. Now our group here, and if we wanted to number it, we need a number where the double bond is. It will be carbon number 1. And when we would number, we need to actually go through the double bond to number. So this would be 1 and then 2 and then 3. So this would be something like 3-methyl cyclopentene. If we went the other way, an acceptable way would be 1, 2, 3, 4, and 5. That obviously gives us 5, which is a larger number. We would not want to go that way. The thing that we cannot do would be to number 1 and then go 2. So when we're numbering a ring structure that has a double bond in it, and I think we talked about it last time, but you do actually have to go through the double bond when you're numbering. So you can't just go 1 and then go to the left there, 2 because you didn't go through the double bond. So you could not do it in that naming fashion. Your only 2 options would have been what we did here. 1, 2, 3 are going the opposite way, which gives us 5. And again, we would want to go 1, 2, and 3. Any questions on that? Just want to make sure I talked about that. I think we did, but just to double check. Okay. So what happens when we add 2 things to a double bond that are not the same elements, our molecules? And that is what is sometimes referred to as an unsymmetrical addition reaction. So in an unsymmetrical addition reaction, works the same way. It just means that we are adding two different guys. So we're basically going to add an H and something else like HCl, maybe HBr. Hydration, we add water, which is H2O. And in adding water, you could think of water as H and OH. You kind of think of that as water. So in this addition reaction, what we do is we break our double bond just like we did before, becomes a single bond, and the hydrogen goes to one carbon and the other guy goes to the other one. So here, hydrogen goes to one carbon, the OH group pretty much goes to the other carbon. And when we do this, we actually get a alcohol in this hydration. So when you add water to a double bond, you get this OH group. OH group is the functional group for an alcohol. So this is one way, that we can add or make an alcohol, is to basically add water to a alkene in this particular case. So when there is no difference in terms of how many hydrogens there are, that's essentially all you do. Break the double bond. Hydrogen goes to one, OH goes to the opposite one. Same thing here. Again, we would focus here. Gonna redraw it exactly the same, except that we will break our double bond and make it a single bond. And again here, hydrogen to one and OH to the other. So here we get an alcohol. This is two carbons. This is what is known as ethanol, OL, in this particular case, based off of our two carbons. Now, these unsymmetrical additions, there is sometimes a case where it does make a difference in terms of where you add the hydrogen and where you add something else. So again, we could have done this reaction, by the way, with, like HBr. Again, the same thing would happen. We would have a single bond. We would put a Br on one and an H on the other. So it works the same way, even if it's not water, something else there attached. But in certain cases, we get this unsymmetrical addition because when we look at this carbon-carbon double bond, there are differences in terms of the hydrogens. So on carbon over here on the right-hand side, this carbon has two hydrogens to start with. Carbon on the left-hand side has one hydrogen directly attached to it. So whenever we add something that's hydrogen and something else, like water, like HBr, HCl, the hydrogen from the water, the HCl, ends up on the carbon that started with the most hydrogens. So what does that mean? You have really two options when you draw this guy. Again, we're going to just basically draw it the exact same way. And we're going to put an H over here to the right, an OH to the left, which is one option in that particular case. We also could have got the exact same thing by adding the OH to the right-hand side and the H to the left-hand side. This actually gives us two alcohols. One is known as 2-propanol, and that is because the OH group is at carbon number 2, which is right here, 1 and 2, and that is where the OH group is located, so that is 2-propanol. And over here, the OH group is located at carbon number 1, and that is one propanol. It actually gives us two different products in this case. And the major product, and the one that you should usually always draw, would be the one where the H ended up on the right-hand carbon. And that is because it started with two hydrogens to begin with. This is what is known as McCarthy-Knikoff's rule. The hydrogen ends up at the carbon that started with the most hydrogens to begin with. This would be our major product. This is sometimes referred to. This is sometimes referred to as the minor product. So you should always try to draw the major product, and it does occur here when we have sort of an option as to where that hydrogen could add. Again, always adds to the hydrogen, is always added to the carbon that had the most hydrogens to begin with. And when we talk about most hydrogens, we're talking about hydrogens that are directly attached to the carbon. Any questions on that? And again, that's basically what this says. Again, it is McCarthy-Knikoff's rule. Hydrogen to the carbon that started with the most hydrogens. The other guy goes to the other one. That will give you your major product. And that's what we see here, as we just talked about. Again, carbon on the right has the two hydrogens. Carbon on the left there has one. So we should put the hydrogen coming in on the carbon on the right because it started with the most hydrogens in that particular case. All right, so why don't you try some here and see what you come up with. So there we go. Why don't you draw the product of each of these and see what you come up with. Okay, let's take a look at these here. All right, so I'm just going to kind of draw out the first, I'm going to kind of draw it out so you could kind of see it all done here and what's happening. So if we drew out the first one, and again, you don't necessarily have to, just might sometimes easier to kind of see things in this particular case. Looks something like this and this. Okay. So here we're going to add water. And again, you could think of water as H and OH. So remember that really we just want to look at where that double bond is. And that's the only thing that changes. Everything else is going to be identical. So you could really draw it pretty quickly. You could just redraw it exactly the way it looks. And again, the only thing really you want to change is that double bond into a single bond. So we'll do that. We'll make that now a single bond there. And everything else, again, remains exactly the same here. And now what we're going to add is hydrogen to one carbon and OH to the other carbon. And when we look at this carbon-carbon double bond, this guy has one hydrogen. This one also has one hydrogen. So it really doesn't matter which one you choose. So if you want, you could put the hydrogen on the left and the OH on the right, or you could do it vice versa. You could put the OH on the left one and the hydrogen on the right one. It actually ends up being the same alcohol no matter which way you go. And that is something like 3-hexanol will be the same alcohol. Again, 1, 2, 3, 4, 5, 6 carbons based off of hexane, OL because it's an alcohol, carbon number 3, where the OH group would be located. And that's how we get to that name there, would be 3-hexanol. Again, in this case, it's really symmetrical. It doesn't really matter which way you do it. You actually end up with the same product no matter which one you do. Any questions on that particular one there? Again, I'm going to draw out the second one because I think it's just a little bit easier to kind of see what's happening. So we'll draw out most of the second one here. I'm going to leave this guy together. And I have my double bond here. Go that way. And we have that. And we have this. Okay. And same deal, we're going to add water here. We're going to focus in again here, and all we're going to simply do is make that into a single bond. So I'll draw it down low, or have a little bit more room, I think. And again, I'm not doing anything fancy to it. I'm not really changing anything other than making that now a single bond. And again, that's really going to give it room to add those guys in. But when I look at my original arrangement here by my double bond, I do have a difference in how many hydrogens are attached to the carbons. The carbon on the right has one hydrogen. The carbon on the left, directly attached to it, has no hydrogens. So the hydrogen here does end up at a particular carbon, and it's important. So here, the hydrogen coming in should end up on the carbon that started with the most hydrogens. So again, that carbon on the right had one hydrogen. Carbon on the left had no hydrogens. So the hydrogen coming in ends up at the one that had the most hydrogens to begin with. And our OH will end up on the other carbon there, giving us in terms of alcohol 1, 2, 3, 4, 5. That is pentanol. Again, OL for the alcohol part. OH group at carbon number 2, that is 2-pentanol. And there's also a methyl group here, and that would be 2-methyl 2-pentanol in terms of the name. But more importantly, any question on the drawing of the product here? And this would be your major product if you drew it the opposite way, where you put the OH on the other carbon. That technically would be the minor product. And again, we should focus in on drawing the major product here. Lastly, here we have a cycloalkene, and this has a hydrogen. This has a hydrogen. And again, nothing here is going to be different. Then that double bond will become a single bond. Nothing weird happens like, the ring opens or anything like that. So it remains exactly the same. So we're just going to draw it exactly the same, but now with a single bond. And in this particular case, same deal. This had a hydrogen to begin with. This carbon had a hydrogen to begin with. It doesn't matter which one you put the OH on. You could go OH here and H on the bottom was perfectly fine, or you could flip it, because no matter which way you drew it, if you drew it the opposite way, put the OH down here and the H up here, they're both really the same thing. They're both what are known as cyclopentanol. And wherever that OH group would be, this would technically be carbon number 1 in each of them. So this would be cyclopentanol. Question on any of those 2 there or 3 there? All right, let's try a few more here. Take a look at them. So give these guys a draw real quick and see what you come up with. Okay, so let's take a look and see how we're doing. So remember, again, even if there's lots of carbons, it looks all scary and all that good stuff, there's only one part of this molecule that's going to change, and it's always right there at the carbon-carbon double bond. And pretty much, if you can recognize this as an addition reaction, you pretty much don't need to waste any time, and you pretty much could just redraw exactly what they gave you, except again, we're going to make that double bond into a single bond. And as you can see, what I just did is just that. I drew it exactly the same, no real difference. Everything's in the same sort of location. And pretty much H2 is adding two H's. And in this case, this is symmetrical, which means you can't really mess it up. You just want to put an H on each of them. And there would be your product right there, which would be 1, 2, 3, 4 carbons, all single bonded, and that would be butane. Yeah. Any questions on that one there? Again, really same idea with the next one and all of these is this is really the only part I'm going to focus in on. I am again going to just really redraw it exactly the way it looks. So I'm going to even kind of do it almost like they have it. I'm going to make that double bond into a single bond. And you know what? I'm just going to roll right through and write everything else the same. If I can see what it says there, I think we got one more. Now, in this particular case, we are adding water, which is HOH. And just to focus a little bit more on where that double bond was, I'm going to draw the H up. So I will draw the H out there. Just again, you don't have to do this, but just to kind of show you a little bit more what we're going to be looking at. So when we look at this, we want to add the H to the carbon that started with the most hydrogens attached directly to it. And in this particular case, it would be this carbon here. As you can see, we had one H that was attached originally. The carbon on the left has no H's directly attached to it. It has a carbon attached to it. It has another carbon attached to it. Remember that the connection here on the left is actually carbon to carbon, and those hydrogens are attached to the carbon. So the carbon on the left here has none directly attached to it. So the carbon on the right should be the one that gets the H. Carbon on the left should be the one that gets the OH in that particular case. Question on that one there. This would be, again, if we were to name this, this has 1, 2, 3, 4, 5, 6 carbons in a row that has the OH group. So that goes from hexane to hexanol. The OH group is at carbon number 2, so that is 2-hexanol. And we also have a methyl group over here, and that would be 2-methyl 2-hexanol in this particular case. More important right now, the drawing part of it. Any questions on that part? Now, same thing here. We're going to just focus in on our double bond, and we're just going to redraw it exactly the way it was there. And I think that means we have a CH3, a C that becomes now a single bond. I'll draw the H up so we can kind of see it. And we have CH3, and I also have a CH3 here. In this particular case, we're adding Br2, which is 2 BRs. So again, you can't really mess it up since it is 2 BRs is symmetrical. You pretty much just put a BR onto each of them and get you something like that's now butane. You got something like maybe 2, 3 dibromal 3-methyl butane in this particular case. And lastly, here we're going to look at this carbon-carbon double bond. And again, if we redraw that, we'll go over here just the way it was. So we got CH3 or C, CH3, CH3. We'll do a carbon. I'll draw the hydrogen. We'll make this now a single bond with 2 hydrogens going this way. So looking at this, this is going to be an addition of an H and a Cl. The H should end up over here on the right, as it started with the most hydrogens. This carbon had 2 hydrogens to begin with. This carbon had 1, and the Cl should end up right about there. Any questions on how to draw these addition reactions, symmetrical, unsymmetrical addition? Again, if it's symmetrical, you really don't have to worry about where you put anything. It's only on those unsymmetrical ones where the carbon-carbon double bond, one of the carbons has more hydrogens than the other directly attached to it. The rule is the hydrogen ends up on the carbon that started with the most hydrogens to begin with. Any questions on that there? Okay, so looking at the time, probably a good place, I guess, to stop. So we will stop here, and we'll continue on Wednesday. We'll get into the next chapter as well. As I think we're nearing the end of this one, so we'll get into I think it's chapter 12 next, I think. Other than that, I will see everybody that has discussion in about 5 minutes or so. Those that have lab, have a good rest of your evening. I'll see you on Wednesday, and discussion will start again in about 5 minutes. And make sure you put here if you haven't done so. And have a good night if you're leaving to lab, and have a good night if you're staying for discussion.